Okay, question 66. Astronauts are using a centrifuge to simulate the acceleration of a rocket launch. The centrifuge takes 30 seconds to speed up from rest to its top speed of one rotation every 1.3 seconds. The astronaut is strapped into a seat 6 meters from the axis. And from this information, we're trying to deduce what is the astronaut's tangential acceleration during the first 30 seconds. So, what is the tangential acceleration during its buildup to its top speed? Not its top speed, but its buildup to that. So, let's pull some of the crucial information that we'll need to tackle this. So, first we're given the radius. As it says, the astronaut is strapped into the seat 6 meters from the axis. So in this model, we know that the radius we're going to be dealing with for the circle is 6 meters. Next is that the delta t, or the displacement of time that we're going to be dealing with, will be 30 seconds. Another thing that we're going to learn is the period time of one revolution, which in this case is 1.3 seconds for every rotation. And so for this, we can just use this equation regarding the tangential acceleration with delta v over delta t. And this will help us figure out the acceleration as it revolves around the center here. So the first things first is we'll need to find its velocity. And so to do that, we need to, our velocity we will get 2 pi radians, because we're going to have to convert one rotation into a certain distance, which in this case will be 2 pi radians, multiplied by its radius to get its circumference, alright? And then we will divide the circumference, or distance that it's traveled, by the time that it takes, which is 1.3 seconds. So 12 pi over 1.3 converts to 28.999, which will just round to 29 meters per second. And then we have our velocity. So then we will then find the tangential acceleration by implementing the 30-second delta t right here. Because we now have delta v, which is 29 meters per second, over the delta t, which is 30 seconds, starting from 0 and going to 30, which leaves us with a tangential acceleration of 0.97 meters per second squared. Now to part B. How many g's of acceleration does the astronaut experience when the device is rotating at top speed? Each 9.8 meters per second of acceleration is 1 g. So we can deduce some of the same information from the first part, like the radius of 6 meters. We can also take into account the velocity that the object has at its 30-second point, which we're going to use the 29 meters per second here in this acceleration for rotational acceleration, which is v squared over the radius, which equals 29 squared over 6, which gives us 140.2 meters per second squared. So it's saying at its maximum velocity, the person around it is accelerating at 140.2 meters per second squared in this circular motion. Now, we have the acceleration, but we now need to convert it to g's. And one gravity, which in this case is 9.8 meters per second squared, as it's specified here, we will split our total into 9.8 increments, which in this turn transforms or results in 14.31 gravities, or 14.31 g's of force, which is incredibly high. But if I'm not mistaken, I believe astronauts experience up to 15 or 16 g's of force when reaching escape velocity in a rocket. And so these are perfect levels of g's experienced to practice going into space.